I will not start commenting.
Yeah. Okay. Super. Could you've got it because we're recording now. Click on got it. Super. All right. Wonderful. All right. So thank you all for coming. Really great to see you all here. So we're really delighted to have Alexander Rothkopf here in person. So he gave a couple of very nice CCNP seminars at the beginning of the year that you can find on the YouTube channel. We're slowly building up an audience, which is really well. Yeah, very good. And so Alexander and I applied for an Erasmus Plus grant. I would say at least 90% of the work was done by Alexander in terms of applying, which we received.
Yes, we finally managed.
The European
Union.
Yeah, thank you very much. Brussels. And then a number of positions post that, and is now a full professor at the University of Stavanger in Norway. Again, really delighted to have you here to talk to us a little bit about complex Langevin.
Yeah, thank you very much, Will, for this kind introduction. It's really a pleasure to finally be here and have the chance to talk to you in person. Monty Python would say, and now for something completely different. In the talks before, in the beginning of the year, I talked a bit about Arconium and open quantum systems. Now I want to tell you about something completely different that my group is working on, and this is our work towards robust real-time dynamics with the complex Langevin. And in this talk, I would first like to motivate what is quantum real-time dynamics. And why it is difficult to obtain the current methods. Then I would like to tell you a little bit about one of the possible methods that are out there to tackle this challenge, so-called complex Langevin, and why that is also not a panacea, but there are difficulties with that. And then in the main part, well, two things that over the past year, my group has worked on how to overcome these methods challenges closer towards determining quantum real-time dynamics from lattice Q systems. And I'm really so happy that Johannes gave us a talk on Wednesday already about lattice QCD and the many successes that have already been achieved. Let me start with a pop culture reference. The final frontier, and it's not the final frontier of Star Trek, but it's actually real science. It's not science fiction. It's the final frontier, in my opinion, for lattice field theory. How do we access real-time dynamics? What is it? What is he talking about? Well, you heard from Johannes about the successes that we already had. You can determine that what you started. You can determine the vacuum masses. You can predict vacuum mass dot patterns. You can predict the vacuum scattering rates and widths of particles nowadays, and you have an excellent access to the thermodynamic properties of strongly interacting nuclear matter. And what some of the experiments are now moving towards is that we want to understand not the static properties, but we want to understand dynamical properties, real-time dynamics, and that can, for example, be transport coefficients. So how does the quark-gluon plasma created in a heavy ion collision, how does external shocks to external perturbations, how do hard probes travel through such kind of a plasma? But also in a zero temperature context, transient phenomena, resonances or genuine non-equilibrium dynamics is something that we don't yet know how to really compute from non-perturbed from first principles. And more recently, the question about so-called parton distribution functions. So how much, essentially very naively thought, what's the momentum distribution of partons inside of protons and neutrons that we also would like to understand. And for all of these, you actually need precision access to correlation functions in Minkowski time. And as you heard from Johannes' talk, well, the simulations in lattice QCD formulated in an artificial Euclidean time, and accessing these Minkowski time correlation functions amount to an exponentially hard correlation functions in Euclidean time that And so essentially, each degree of freedom in your system, let's say we have field degrees of freedom in Euclidean time that was your field living on this contour part down into the complex plane. At each point, what it now does is you set up a stochastic process in some artificial extra time that we call tau Langevin, and you carry out a stochastic process that is governed by the action of the system, SE, and a Gaussian noise. That sounds very arbitrary. Why are they introducing some new time direction? What is going on here? The point is that you might have encountered before that you can describe stochastic processes either on the level of the realization of the system itself or on the level of the probability distribution that these the stochastic variables obey. And you can take such kind of a process and you can either run the evolution of your system variables directly, or you can look at the distribution, the probability distribution of these degrees of freedom, and they evolve then according to what is known as the Fokker-Planck equation. The details of that equation are irrelevant. The important point is that you can use this Fokker-Planck equation to prove that as you let your variables evolve in this fictitious Langevin time, the probability distribution for late Langevin time will converge to exactly e to the minus st. And e to the minus st is exactly the distribution that your field degrees of freedom should obey to be used as input for evaluating a package. So what you do here is you can think of it really just as a mathematical trick that you introduce a stochastic evolution that is cleverly set up such that after running this for a long time, your field degrees of freedom are distributed exactly as they should be through your path integral. Okay, so all this setup works if that thing can be interpreted as a probability distribution. Now, what I wanted to tell you is that, well, what we're actually after is not an integral that has a weight e to the minus s, but we wanted to evaluate an integral that has a weight e to the is. So you can be very bold, or and simply say, well, if this kind of process has served us well, why not replacing this drift term governed by my action by a complex drift term? And if you do that, even if you start out with a real valued field phi in the first step, in the next step, you would get a complexified field phi. So this replacement going from a real S to a complex action requires you to also complexify all the degrees of freedom of your theory. And then what you end up plugging all of this in is you get two stochastic processes. One for the real part of your field and one for this imaginary part of your field. And the hope is that the actual expectation value of your system is still obtained from evaluating or taking the average over the observable, now evaluated in this complexified field. That is, yes?
Doesn't matter whether you put the noise into the real part or the imaginary part.
Yes. So that's why. So you can show that in this naive formulation that I show you here, you only have noise in the real part. And you can actually show that it breaks down if you put noise into the imaginary. Now, then you should ask why. Okay? And I will not be able to answer you this because that would require me to tell you why this replacement is actually, let's say, admissible. And that's the big thing, that this is just a guess at this point. And we don't have a systematic derivation of these equations from this. You can show that if you do only real noise, in some cases, you get this out, but there are also other cases where it doesn't work. And so then people have, and this complaint, people have found and now understand what is the criterion when it works and when it doesn't work. So at the moment, take this as a very adventurous recipe to sample systems with a complex action.
I'm sorry, just to
Yes.
sort of maybe you're being very conservative. So I imagine you're going to show us some results where you compute, expectation
Yes.
values using this. In those situations that you're going to show us, are we assured that the criteria are satisfied?
Yes.
Okay.
Yes, they are. And well, if you're adventurous, usually you will run into pitfalls very quickly. And the first thing that people found that happens is that their simulations simply diverge. So you try and evaluate this over your artificial Langevin time, and your system spirals out of control. Okay, so people have been trying in the past to keep this at bay by somehow changing the step size, the simulations, to somehow keep this under control. And the other thing that is then more related to your question of how can I be sure that this actually works is, well, a priori, you cannot be sure that it works. So this would be, it's a model, this is the correct solution, and this is, or a certain parameter set, what complex Langevin gets out. If I hadn't drawn the black lines, you would not see any pathology that indicates to you that these lines are not correct. So what to do? And essentially, there is there's now a posteriori criterion that you can investigate the histograms of your observables and your field degrees of freedom, based on which you can then decide, can I trust my simulation or not? But you cannot say, I give you a parameter set and you tell me a priori it will work or not.
So here you're convincing us that it is not worked by having the black line, the true solution. Yeah. So when you don't have the true solution, do you have some?
Yes. So you would look at the field degrees of freedom, and essentially the trick has to do with carrying out a step of integration by parts in some connection. And integration by parts always asks you to look at the boundaries of your system, and it only works if you can neglect the boundary term. And if the histograms of your field variables die off too slowly, so that they extend far into the complex plane, then you cannot throw away those boundary terms. And this is then the criterion that you would find. If you see that your simulation gives these fat tails for your field degrees, you would very likely not have converged to the correct solution, because it breaks this integration by parts step that hides somewhere in the proof of correct convergence. Okay, let's have a look first at these problems, because this was the first. So in our group, our mantra is, okay, we cannot change the world immediately, so let's try and attack one problem step by step. And so we only focus on the problem of the runaway solutions here. And so this is your standard complex Langevin equation, Gaussian noise plus this complex drift term. And if you look in the literature, how do people discretize this? They use the good old explicit forward Euler. And that is that you discretize your Langevin time derivative by a forward finite difference. And well, the fact that a explicit solver leads to these divergences is something that people in other communities have long known to be a problem, and they've associated with the concept of stiff differential equations, which there's not really a agreed upon definition what a stiff problem is, but the practical definition would be the one that explicit solvers can't robustly tackle. And so from works on PDEs and computational electrodynamics, we know that in that case, implicit solvers can help you. Yes?
Was this runaway illustration still for the harmonic oscillator?
That might even be for the harmonic oscillator, yes.
Okay. The reason I'm asking is when you think of the classical system.
Yep.
So going classical, but very stochastic.
Mm-hmm.
We know that solutions are bound. Now I wonder this asymmetry between the real and imaginary form by would that break this criterion that
so as long as the underlying path integral is well defined, there should not be divergent trajectories.
Because you drive one degree of freedom,
yep,
and let the other be driven indirectly.
But it's still coupled such.
It's still coupled.
It's still coupled so that it cannot run off. So therefore, well, what we looked at the Bible of numerical stochastic methods, and what they tell you on chapter 3 or so. Well, take a look at these kind of generalized Euler schemes, so-called Euler-Maruyama scheme that now has a explicit part, because here you evaluate the drift term with the fields at the current time step lambda, and it has an implicit part where you evaluate the drift term from the field at the next time step that you of course don't know yet. And so to solve this equation, you need a self-consistent determination of this field value at the next time step. Now you could say, okay, this is the first, the lowest order discretization. Why am I not showing some Runaway fourth order thing here? If you have a stochastic differential equation, if you want to derive a systematic higher order scheme, you actually have to not just improve the drift term, but you actually get additional noise terms due to Ito calculus that then quickly become very complicated to actually implement and evaluate. So these lowest order schemes, even though the convergence properties are not great, they are usually a very good compromise in efficiency. Okay, and so just to give you an idea of how these implicit and explicit methods differ. So we have we initialized the system at a certain point and then used either explicit, that is theta equals 0, then you only have the explicit term, that's the red curve here, or theta equals 1, then you have only the implicit term here, that's the violet curve here, or theta equals 1/2, which is the so-called semi-implicit scheme that's similar to this Crank-Nicholson scheme that you might have encountered. And what you see, so in green is the true trajectory, and you will see that the explicit scheme has the tendency to overshoot, while the implicit scheme has the tendency to undershoot, while the semi-implicit scheme sits almost perfectly on that trajectory. And so if you since this Euler-Maruyama scheme has, whether it's implicit or explicit, has the same order of convergence, so the same accuracy, you will do the same magnitude of error with the implicit scheme and the explicit scheme. The only difference is that the implicit scheme is actually unconditionally stable because it's always undershooting, it doesn't run off, but that doesn't mean you're not making a similar or error of the similar magnitude as your explicit scheme. And you can see how this works in the free theory. So for the harmonic oscillator, where you can still run off even with the harmonic oscillator if you don't do implicit schemes. And the good thing in the free theory is that your action is very simple. It's just quadratic in the field. So you can just plug this in, take the derivative, and you get a matrix equation for this update step. And the only important point is this. Let's look at the absolute value of the next step expressed in the absolute value of the field at the current step. So if you have your theta equals 0 in explicit scheme, this is gone, and you have something 1 plus something. That means this magnitude will always be a tiny bit larger than the previous amplitude, and that tells you immediately this thing will run off. If you have theta equals 1, it will be 1 divided by 1 minus something. That absolute value is smaller than 1, so you will always have shrinkage. And if you do theta equals 1/2, that thing will actually have magnitude exactly 1. And so you can really see that the semi-implicit scheme is ideal when it comes to stability properties and accuracy properties. Okay. So now I told you about, you get a stable evolution if the underlying path integral is well defined. But I talked about somehow formulating our physics on the real-time contour. And if you were to do a perturbative computation, you would have to put an I epsilon somewhere to damp out this highly oscillatory behavior over time to make sense out of this path integral. And yes, it's always there's a not. So if the field value is large, the drift term is large, and it's large compared to the magnitude of the noise. So once you go outside in the field space, the noise is not that important. But as you come closer to the origin, the noise starts dominating. That's just a coincidence. It could have fluctuated in some other direction. And so you somehow have to bring in a small I epsilon into your action. And what people usually do is they actually tilt the contour because in your action the contour step size shows up as AJ. And if you now tilt your contour, you give it a small imaginary part that actually you can pull outside so that on this tilted contour, the action you have is the original action plus some term that is positive with plus I, so that it then gives you a minus real R. The difficulty with this is that you started and you wanted to compute correlation functions on the forward and backward path. And now you're able to compute correlation functions on some funny tilted thing here and a horribly tilted path here. So if you wanted to, for example, you wanted to compute a spectral function that is a correlation function of a phi plus phi minus field, you would not be able to get that out of here because that is not on the real-time contour anymore.
Sorry, why did you make a triangle? So I understand you tilt.
Yes.
And then can you not come back and then stay near the real axis?
You could, but then the system becomes, again, stiff. The complex Langevin evolution becomes stiffer and stiffer because the regularization is smaller and smaller. And so people simply have said, oh, let's tilt it
maximally.
Maximally, yes. So you have to come back to this point so that your KMS relation is fulfilled, so that this point and this point are identified. But if you wait for the next slide, I will come back to the actual Schwinger-Keltisch contour that we wanted. And so here, because you can say, well, maybe it doesn't matter if I just want the correlator on this forward contour by itself, then yeah, this is a simulation on this tilted contour. And you can see, well, if you're at very small real-time extent, then you're still quite close to the true solution that is this black line. But again, you can already see that it is starting to deviate from it. And if you want to eventually do long-time real-time simulations, this tilt will always drive you away from the true solution that you're actually after. And this is another benefit of these implicit methods, because the implicit method offers an inherent regularization itself. So if you take the update prescription, and we only did it in the free theory because there we can actually show what's going on. Again, you plug in the implicit term, gives you this 1 minus I epsilon theta m inverse from the other side. You just multiply it out, and then you see that from the point of view of an explicit scheme, if you interpret this as an explicit scheme, that would correspond to the standard action or the standard drift term plus a correction of your drift term that actually looks again like something, you're adding something to your action that is positive and goes with plus I, so that this becomes, or this has the appropriate form to take the role of a regularization term. Without having tilted anything, just the solver itself introduces this regularization. And that means we can now actually stay on the actual forward and backward contour and then go down as you suggest. Interesting thing is this regulator depends on the step size. So on the one hand, you want to make the step size as small as possible to be as close to the true solution of the Langevin, of the continuum Langevin equation. At the same time, the finite step size actually gives you a valuable regulator. And so now you have to figure out what is the trade-off. And the good thing, and the argument I would like to make is that with the tilt, it is very difficult. We have not found a way how to correct for the effect of the tilt. You really get a different correlation function, but maybe there's a way how to correct for this step size dependence. And this is just essentially the action. So this is, you take the derivative of the action. That's the m, and then you get m squared. That's just a funny notation we use. So essentially, if you just look at this one here, that is the relevant one, you get something that looks like the standard action with the correction term.
Clearly, this imaginary thought is what you want to have. But say you feel a bit nervous about the dependence on the discretization details and also on theta.
I love it, actually, because in the next step, I will show you that with an educated guess, we found a way how to correct for the step size dependence. So, and I too am running out of time. So it's a good tradition of external speakers. So essentially, the standard way of estimating finite step size corrections is by, again, looking at the Fokker-Planck equation, essentially, and trying to rederive the Fokker-Planck equation, where you say, okay, the probability distribution at the lambda plus first step in Langevin time is given by the probability of finding the field at the previous time step times the delta function that fixes you to the next field to take on the value that you get from your update prescription. And in the continuum, that would be the continuum Langevin equation that gives you this update prescription. Here you can use the discretized Langevin equation, and then you do the work, and you can show that this corresponds to a modified Rothkopf equation, where the term here, this action, is now the continuum action plus a correction that depends on the step size. And then you can ask, at least in the free theory, we thought, okay, let's again be bold and make this is all derived for the real Langevin. Let's make a bold move and turn this into an expression for a complex action, and we would get this kind of correction term. And then you can ask, how would I have to modify my field phi so that if I plug in the field phi into this S, it would counteract this correction term. And you get that, at least in the free theory, you should use this kind of correction term. And since I'm really running out of time, let me just show you one example. The red or these purple squares show you some measure for the actual deviation between the continuum Langevin result and the discretized time step Langevin result. And the green points are actually our estimate of this correction term. And so that if the naive simulation gives you the green curve and the pink curve here, you can now correct for this and get the blue points and the red points that lie exactly on top of the correct solution, as long as your time step is small enough. So so, and if you give me 5 more minutes, I will try to motivate one more point. So what I've tried to show you now is we have this bold recipe to try and simulate physics in Minkowski time that requires you to solve a stochastic differential equation in complexified field degrees of freedom. It showed divergences. We now know where they come from. It's simply a numerics artifact. If you use implicit solvers, they're gone. But if you now, I only showed you results on very small real-time contours. What small means? Let's say 0.5 in some units. It's some unit. The thing is, if this is an anharmonic oscillator, we haven't even seen one oscillation. That is essentially the measure by which you can, if you want to extract anything relevant from such a simulation, you should be able to simulate multiple oscillations so that you can, for example, understand the damping of the amplitude, for example. So here we are far away from that. And so on these small time extent, we get very nice results for the real-time correlation function and the Euclidean time correlation function. In the following slides, I will use such kind of a summary plot, which this is the forward path correlator, this is the backward path correlator, the Euclidean correlator, and this is the equal time correlation function that should just be constant everywhere. And now let me extend this from 0.5 to 1.0. And this green thing, for example, should be the constant. And again, no pathologies. If I hadn't shown you the black curves, you wouldn't say anything is particularly wrong with these data points, but they're completely away from the right solution. If you were to check the criterion that I mentioned before, you would see it's not fulfilled. This is not the solution you're looking for. The point is, okay, now we know that it's not the right solution. What do we do about it? And what we try to do is to modify the evolution of the Langevin equation in this form. So there's a certain degree of freedom that you can reshuffle dynamics from the drift term into the noise and vice versa. And that is through a so-called kernel K that you can that you can introduce in this fashion. So it multiplies the drift term and it introduces a square root of that k for the noise. And what people saw in very simple models is that if you can manage to render the drift term completely real, that somehow restores the correct convergence. And this is why we looked at the free theory again. So you see that the green curve is still off.
Much better.
Much better, because the free theory is always much better. And here we can, so we go to 10. So in the free theory, it is already better, but it's still bad. And so we looked at, okay, how can we find the kernel that makes the drift term completely real? Well, you take the inverse propagator, and then your drift term just becomes -5. And then you have to take the square root of this thing, put it in here, and if we do that, that does it. Okay, free theory is maybe not so impressive, but at least it seems to be able to do something. Now we can ask,
Well, it's systematically above 1. Should it be 1 or just constant?
this one should be above 1. This is it should have a certain value that is given by the zero real-time correlator, and then it should just be constant.
Okay.
And well, we can try it again. I've told you to be bold several times now, so why stop now? You can now try and take the interacting theory and use the same kernel. And this is just the example for this, because there's already too much shown here. So this is the function that should be constant. The blue points should be constant. And then you introduce this kernel, and they become relatively constant. And so that means you can actually restore partially the correct convergence up to extent 1. So we've already doubled it by naively taking the free theory kernel and using it for the interaction theory. But that's some of a stroke of genius method, in the sense that there's no systematic recipe to improve this. So how to do that? Well, so what we thought is, okay, actually we don't need to reinvent the wheel for everything, because we have access to a lot of information beforehand. From our from standard Euclidean simulations, we know what the correlator is in the Euclidean range, and we know from the symmetries that this thing should be a constant. So the thing that we really are after is the real-time two-point function that we don't have access to a priori. And so what we thought is, can we actually find systematically kernels that restore the correct convergence by telling them that they should actually restore the convergence of the complex number to the known observables. And since I'm really out of time, let me just say, we set up optimization functionals that contain the values of the Euclidean correlator and the values of the equal time correlator that we know that have to be constant. And we ask, please find the values of the kernel that minimize this kind of optimization functional. And if we do that, so we use a constant kernel, that's the simplest kernel. And this is, you've seen this now multiple times, that's extent 1, real-time extent 1, where it fails. And now we try to find a kernel that optimizes this functional. And for real-time extent 1, I think we're doing already a good job. Then we do it to 1.5. You can see that the naive simulation becomes more and more horrible. It goes away from anything that is relevant. But even at 1.5, we're able to get relatively close. Mind, this is the simplest form of a kernel. So this is still not the most expressive one, but all good things come to an end. If you go to real-time extent 2, oopala, now it also breaks down. So we're able to extend the convergence of complex Langevin by a factor of 3 compared to what was previously done by Berges and Sexty, but it's not black magic in the sense that it also breaks down at some point, potentially because our kernel is not expressive enough. And maybe if anybody is interested, I'm happy to talk to you about this afterwards. We have an idea of why this is the case, because essentially the kernel, the constant kernel, if you have more than one critical point in your system, the constant kernel can only select one of them, and you cannot combine the physics of all these critical points, and therefore this is too limited parameterization of the kernel. And our work, this was the explanation here, our work has to then be, can we find cost-effective optimization strategies for more expressive kernels that, for example, depend on the field degrees of freedom themselves. And with that, thank you for your attention.
That was really great. Thank you. There are a number of questions during the talk.
Yes.
But are there further questions? No, yeah.
So from this quick one, what do you mean by an expressive kernel?
Say again.
What do you mean by an expressive kernel?
Essentially, at the moment, the only way how this, so we have one constant matrix multiplied to the drift term at all Langevin times. Of course, this kernel could depend on Langevin time. So you could, depending on, if you think about the neural network playing the Atari game, if you were to, this needs to adapt over time to fulfill this minimization functional to win the Atari game. And similarly here, you would need a kernel that reshuffles from the drift term to the noise term differently at different steps in the evolution. And we can't, with the one we have, we can't do that at the moment.
Okay.
So if you go back to
Sure.
the slide where this I am inverse times as a kernel, I think.
Yes.
That was for the M inverse of the free theory.
Yes.
Could you, with the field that you currently have, include the M inverse contribution at each time step and try to apply that?
Mean field like.
Yeah, you could do things like, so one thing that I didn't mention is that, for example, for the interacting theory, we then tried things like, can you change the mass in the kernel, in the free theory kernel, to somehow mimic what the interacting theory might do, and that indeed even gets you even closer to the correct result. So this is a very good idea that you could use more approximate.
I'm saying to somehow encode the dynamics of the system on the type of noise that you get in the
Yes.
systematic
Yes.
noise, right?
Yes. It's still one noise source that now gets somehow distributed between real source and imaginary source, but exactly as you say, it's not that you only have real noise anymore.
So you should.
Yeah, we go ahead.
Okay.
It's actually, I think, in
Previous one? Yes. Yes.
Then you have this feature that diode between the
Yes.
the previous sort of kind of
Yes.
Then you have this weight. I mean, you compare it and you said, okay, this sort of kind of semi-explicit ones. Can you demonstrate that it's reflected into
Yes.
we have quadratic, we have an action that is
Quadratic, yes.
That thing. So does that so does this fact that like the semi-implicit ones that kind of average this times they generically
Yes.
form
So
more exotic actions?
well, for deterministic systems, this is how you construct the first higher order scheme. So if you have an Euler forward or backward, it's order dt. And if you then combine the forward and backward Euler step, you get a scheme that is order dt squared, and that's your Crank-Nichols potential. And this is a very similar train of thought that happens here for the semi-implicit.
Yeah, and so can one write like such a formula or more complicated?
No, you can usually not write it in such a nice way that because it wouldn't. So the magnitude in the interacting theory is not necessarily preserved. So that's the thing. In the interacting theory, the next time step could be whatever it is, but in the free theory, you should actually have the same magnitude from one time step to the other. And this is why here it's just a nice way how to explicitly show that if there's a change in the magnitude, it comes from your discretization and not because the physics would not change.
He has actually experience doing Langevin and Rothkopf on curved manifolds.
Oh,
where
really
you have
interesting.
Where you have quite a bit of control just out of the geometry over what you do in these terms,
Nice.
and actually playing there with moving a time step around actually changes just the stochastic term quite a bit. So you can move things around and you actually flip the sign around in these terms, like yeah,
Really?
absolutely. Yeah. By changing the way you do your stochastic step. So comparing that to what you're doing might be a cool little project.
I would be very interested because actually, if you were, we're doing only the baby systems here with Taylor and everything, but of course the actual interest of this community lies in doing SU3, and then you have to design a stochastic process on an SU3 manifold. And again, it seems very interesting.
Can be done just right.
Cool. Sounds good.
But for a simpler system,
Yeah.
I mean, just diffusion on the group, but maybe there's something wrong.
So thinking about something completely different.
Sure.
You think hydrodynamics,
Yes.
which is also numerical
Mhm.
challenge, different discretization schemes and complicated and all sorts of issues. And one of the tricks or one of the observations made is when you discretize, you sometimes or on purpose that you do introduce some viscosity, and that stabilizes the system. Do you see some connection?
In that,
I mean,
so usually the reason why people use this viscosity is because by that they believe they can save an explicit scheme. And I don't know, maybe this is why I don't then get things done, because I would then say rather you should use an implicit scheme, which is of course much more expensive usually, and that's why people don't use it. But if you then use an implicit scheme, you would not need to add these extra viscosities because you get the regularization for free and you get the stability for free. And so I'd be happy to talk about this because in a different project I've been working on so-called summation by parts finite difference operators, which are constructed such that they exactly mimic the integration by parts of the continuum theory, so that you can, in some cases, somehow much more directly derive discretized equations of motion from the continuum theory, but they lead to implicit schemes. So I think once you introduce these viscosity, it's like you always then have to, of course, systematically determine what kind of physics changes you introduce. And,
Okay, there was a question from Blessed on the chat. I guess this is in reference to near the end when you were showing the plots with the uncertainties on them. going out for the various times.
Maybe
Yeah, I think this
here or
would
something.
be good, yeah. And the question is there a particular reason why the uncertainties are more pronounced at p equals 1?
The uncertainties are more pronounced.
I mean, maybe if we look at the top right plot, the green, the sort of the uncertainties are getting larger around t is 1 versus earlier by squint.
Yeah. So this is a question for the technical connoisseur. I believe that in the formulation of the underlying action, there is actually the community is not doing the discretization of the action, right? Because exactly of this integration by parts issue. And so this is why you also see that somehow in the naive simulation, all hell breaks loose at the point where you're turning back. And so what do you do with your derivatives at the point where you're actually going from the forward to the backward direction? And the naive way is to just treat it as a periodic boundary, as a continuing path. And I believe that we have to actually do this slightly differently. But this is a special point. This point is the point where the forward path goes into the backward path. And I will leave it at that. That this is there is some reason why I believe that the errors are specifically large there, and it has to do with the discretization of the derivative at the point.
Sounds delicate.
Sounds like one should have done it before doing the rest. Yeah.
Okay. Super. Any last questions? All right, so let's thank Alexander once more. Really great, thank you.
It's